It's dedicated to our crew. Not only the crew that you see here, some of which are no longer with the program, and there's some other staff that we've hired recently, but also the men and women of the Union Pacific. Imagine having an opportunity to work on a steam locomotive as your full-time occupation for a Class I railroad. And we're all very proud of that. So we're proud to have them standing behind us. Every department on the railroad in one way or another supports us. Some of them on a very regular basis, and sometimes not so much. But a lot of folks in the headquarters building know us, and we know them, and we're very proud to represent them, and we're proud to operate and maintain the locomotives and the passenger cars. This picture, you might recognize it from the last presentation. This is the day we arrived in Cheyenne. Now, we're not going to talk much about the 4014 directly. This presentation is geared more toward what we've done over the last year and a half with the 844. And we'll go into what we're doing. Now, naturally, the design of the UP, the big Alco steam locomotives, there's a lot of commonality. So a lot of the work that we're doing, the materials we're making, the processes we're developing, all of that, of course, ties right into the 4014. We bought a lot of supplies, a lot of equipment, a lot of material, a lot of stay-bolt stock, even some Firebox plate that is directly for the 4014. We're working on tenders, tender wheels, trailer truck wheels, engine truck wheels, you know, all the various things. Very soon we're going to be making the fuel tank for the oil conversion for the 4000. So there's a lot of projects running concurrent with what we're doing. This is also dedicated to my best friend, Ed Gerlitz. Good old Ed. He was responsible for my interest in steam beyond what I had as a childhood interest. And now we're just going to dive right into the 844. In 2013, we discovered a condition in the boiler tubes called over-rolling. And the tubes got rolled. And unfortunately, there wasn't really a good practical way for us to determine the extent of the thinning of that tube wall. So that's a real vexing question for a person in my position, is what do we need to do now? When you've got a small number of tubes leaking, you address them in such a way as to correct that leakage. But when all of the tubes get rolled, that presents a problem, and it could duplicate the scenario that the locomotive endured previous to that.
What do you mean by roll?
The tubes are expanded in a locomotive boiler. A mechanical process known as tube rolling. There's a couple of different processes, but the common steam engine process involves a special rolling tool with a series of small tapered rollers with another tapered mandrel. And that device is installed into the inner diameter, the inside of the tube, and then that mandrel is rotated. And those tapers engage, and as they do, they expand those rolling rollers outward, and they mechanically force the wall of the tube against the ID, the inner diameter of what we call the tube sheet. There's not going to be a test afterwards, but I'll point these out as we go through some of the photographs, and it'll make sense to you. So the process of tube rolling, it's not that scientific. There is a feel to it, like so many things in steam locomotive technology, restoring old farm equipment, hot rods, aircraft. There's a feel to it. There's a lot of old books out there. There's processes. There's official processes that the railroad adopted, and that's what we use. We like technology where we can get our hands on it, where it's applicable, and we've purchased a lot of new equipment, rolling motors and tube rollers. All of those things we've purchased to give us the best possible advantage. Also, a lot of the material that we have in the shop comes from the steam era. And you know, most things mechanical have a limited lifespan. So this is the condition we discovered on the 844. As we began, we were initially just going to take the tubes out of it and simply replace them. And then, yes sir?
Could you kill that set of lights on the front?
Well, I think
the overhead?
Shut the door.
How's that?
Thank you. Much better.
See color. So as we started to get into the process of just taking the tubes out of it, I made the announcement to our bosses that we've got a condition that we want to remedy. We're going to need to have the locomotive down for a while, and that's expanded into a full-blown 1472 inspection. It's a federal regulation the locomotives have to go through every 1,472 service days or 15 years. So in the process, this is what's kind of led to that. There's some parts right here, which is what's left over, some sheet metal that was placed underneath the jacket, and this insulation that really became problematic. With the jacket, the way that it was built, it allowed a lot of water to get in there, and that jacketing, which is a fiber blanket, would retain that moisture. And it was just terrible with that pressure vessel, the outside part of the boiler. Because not being painted, now it can rust. And just some more things. These are sand pipes. And again, you know, it's always a tough call when you've got a historic piece of equipment, a legendary locomotive like the UP844, the 3985, the 4014. You just don't start replacing things just that easy. You know, you think about the historical side of it. Some would say that it looks neat having a bunch of dents in it and the old rough look to it. But there comes a time when you need new equipment. This particular sandpipe's seen better days. It's just about worn through. And that's pieces of the cab. You can see more of that insulating material in the jacket, kind of pop riveted together there. And this was one of the worst days I've had. This is the actual steam dome. That's a close-up of the extent of the corrosion. These are the top studs that secure the dome cover. So you can see this heavy corrosion. And what you're looking at is you're looking at metal that's going away. And as that metal goes away, that reduces the thickness of that pressure vessel. So now we have to start doing some pretty serious analysis, taking measurements, running calculations to verify that that metal plating, not just that, but the entire boiler structure, can still withstand the pressure plus the safety factor. And there is the jacket as well. This particular part of the locomotive was problematic because the sand dome is right up here. In the sand pipes, you can see we're connected with a rubber hose connected to the sander. And that rubber hose, unfortunately, deteriorated under the environment of the steam locomotive. So that hose had broken apart and the sand was leaking out and just completely covered that area. So this area right here was just covered with heavy scale, heavy rust. Another really sad discovery is we started taking that insulation off. We lifted the sand dome off, and now we got to completely expose the entire pressure vessel and remove all the piping, remove all the turret valves, remove the top check, remove everything so we can look at every square centimeter of that pressure vessel.
How thick are the walls of the vessel?
It depends on where it's at, but they're quite thick. And this is an area along the combustion chamber, and the locomotive was equipped with a Wilson sludge remover, and it's a centrifuge that operates as you function or you operate the blowdown valves, and it's designed to dissipate a lot of that pressure and not deposit it track side. That's just a process that you have to proceed with when you're operating the steam locomotive. So the design is that that water, the effluent, comes out of the boiler and it goes through the centrifuge and releases pressure, but all of the heavy sediment and the moisture will be diverted down trackside. Well, that particular component was just through age and deterioration, didn't really function. It would deposit that water right on that jacket where it would easily find its way through that jacket and then continue to saturate that. So right beneath that location on the combustion chamber, the wrapper sheet, the part of the boiler, and I'll point that out on the next slide, was heavily corroded. And we've got more various things that we found, some studs and some bolts welded to the side of the boiler. You can see right above here, that's a remnant of a weld with a bolt welded to the boiler. And that bolt holds something. So that weld, it's not much of a weld, but it's still, you know, it needs to be more secure, and it shouldn't be located adjacent to that cap there. And if I could just ask, we'll have a really in-depth question and answer segment toward the end, if that's okay with everybody. We took the cab off and we found all kinds of things under the cab floor. And yeah, that's a nice snap-on wrench. I wondered where that was. And unfortunately, just through time, this happens with all machines and all equipment. That's a lot of rust, and a lot of saturated metal particles, a piece of welding rod, and various things. But unfortunately, that's laying against the outside of the boiler, underneath the cab floor, that you really can't see. And when that gets saturated with water, that just continues to expand that corrosion. Another really unfortunate condition that we discovered was the water glass drains, and what we call the injector telltale. They had copper lines that were cut off short and were depositing that water on the back of the boiler. So that was just continuing to saturate that outside of the boiler, and worse yet, that water would go through what we call telltale holes, again I'll point those out, and saturate the inside of the firebox behind the refractory. And that's what led to the next set of discoveries we'll talk about. Some electrical conduits, just a matter of disassembling everything, a lot of piping, the jacket pop riveted together, you know, just not that secure in terms of protecting it. And another thing we discovered was the dreaded A word, asbestos. So we had to perform abatement operations on the 844. So we had to stand down and remove that from the locomotive. That's a special team. We're not doing the work, they are. And here's the cab deck. We're starting to take the locomotive apart, and again, you've got to take everything off of it. Well, on this design of locomotive, just like the Challengers and the 4000, the cab is actually attached to the back, or what we call the back head, and then it's got these big braces. All that has to come off to expose the back part of the boiler for us to do the analysis we have to do. And here's another decision. As we put something like that back together, how do you do it? When you've got old deteriorated parts, a lot of cases they've been torch cut and holes torched in them, and they may not line up just, you know, when you put it back together. Or the underside of the cab. Inside the cab, you know, bearing in mind that the locomotive has been in service since 1944. This locomotive has not been retired. So what you're seeing is a locomotive that's been putting in really good service over the years. So we're proud to say that it falls to us to make decisions on what parts of it we're going to try to really keep original, but we also have a good opportunity to really fit her out with some really good brand new steel. There's the cab deck. This particular side is right behind the fireman. And if you could see a close-up of it, it's just tremendously rusted. And as rust gets down in these riveted joints, that rust corrodes, and it's quite strong. And as it does, it just separates the metal, and it bulges up, and you can see all these stratified layers of rust, and it just continues, and there's almost no way to stop it. You can't paint, you can paint over it, but you're not going to stop it. Well, there's the new pieces. And in today's era, my foreman, Austin Barker, he's all things mechanical, all things railroad. We're very, very fortunate to have him and our entire staff. And he can take and draw that on CAD, taking our official Union Pacific Historical Society blueprints, and put that right into CAD, and we can send that file to a local steel shop, and they can use their very precise processing equipment to cut out exactly what we have there. So that's about the extent of how we've outsourced this job. We've done everything else. So we can really get a lot of good material coming in, and all we have to do is assemble it. So it comes complete with the holes already drilled in it. All we need to do is take the piece of T-iron that I was talking about and drill it and ream it and get it ready for riveting. take out those bolts, replace it with a hot rivet, and move on. Took us about 2 days to rivet all that together. And here's that piece that I just pointed out here. You can kind of recognize that. So understanding that the original components lasted since it was built, imagine how long this will last. As we put those pieces of metal, we actually installed some tar paper. That's kind of a technique you use on metal tanks, and you warm that up, and the tar melts out of that tar paper, and it saturates the metal surfaces and protects it. And then you paint it, it's riveted together, and it makes it harder for that water to get in there, which will eventually do what water does to steel. There's a piece, this particular piece is behind the elephant ear. And again, how do you put that piece back together? Which hole does the bolt go in? I forgot. You know, it's bent. It's seen many lives of, many years of service. And again, we look at the locomotives as this wonderful piece of equipment that we're really careful with. We operate it just the way it was operated. Back in the days, this was a utilitarian machine. There was 45 of these. And it had a job to do, and that job required that it had to be out on the road making money for the railroad. So the time it had in the shop had to be just get what needed to be done. And the craftsmen and women did a fabulous job maintaining these locomotives, but there's a whole shop full of these locomotives that got to be maintained. There's a new piece right here with some new welded doors behind it. These particular doors access the lubricators. So when we service the locomotive, you climb up behind those elephant ears and you open those little doors, and that's how you refill the lubricators. So we've had problems over the years. The doors didn't work too good. One of them was cut in half, and that would let dirt and everything get down in there, and you'd have to clean it off, and the dirt would get down in the lubricator. So we kind of made a few little adjustments to make it a little bit easier for us. Now the boiler's coming back together. Things are looking good, but you can see all of the stay bolts, 154 stay bolts on both sides, and all of the rivets down below, all the way around the backside. That was all behind the refractory, the fire brick inside the oil burning firebox. The worst, as I mentioned, the worst part of it was the water glass drains and what we call a telltale for the injector. An injector on a locomotive uses live steam to put water into the boiler. And this particular design, when you're operating a steam locomotive, it's quite loud. And these injectors are the state-of-the-art 1940s. You can't always hear because of the noise of the locomotive when the injector stops working. So it has a feature known as a telltale. It's a small copper line that comes into the cab and deposits into a small little funnel. And then you hear that thing squirting. Sometimes you feel it, you don't hear it. And that's an indication, hey, that injector, what we call broke. It's not delivering water. So the telltale serves a very important function. The drain to that telltale should go down below the level of the boiler and deposit that water where it can just get on the trailing truck or down on the track. And regretfully, it was depositing into the back part of the boiler, and as I said, going through those telltale holes. So as we started to take the firebox apart, we peel back that fire brick, and when we're done talking, you can come up and look at the plate. That's what we discovered. Bearing in mind that that plate has to withstand 300 pounds per square inch. This is the top part of the boiler. These are where the safety valves go. Some patches. I apologize for the photograph. It seems much clearer on my screen. There was a roof sheet patch, some really good quality work that was performed ending in 2004. Some more patches. All of these stable caps, every last one of them had to be replaced. A series of other caps that we'll talk about. These two reinforcing plates are what's known as the turret valves. And they take steam out of the boiler and they run all the various accessories, the water pump, the air pump, the dynamo, the blower, the atomizer, the tank heaters, you know, all of the auxiliary steam that's used from the locomotive. So those valves are really important. you have to be able to operate those valves. They're part of an annual inspection. They're part of a daily locomotive inspection. And so it's important that they operate so that you can turn them off if there's an issue. We replaced over 150 studs. Anything from a handrail bracket to something more substantial, such as the turret valve flange studs, the top check studs. I mean, just enormous amount of studs. And to do that requires just diligence. And this is work that, we're not going to be done next week. We put together a really comprehensive timeline. We've got this really wonderful Excel spreadsheet that is itself a work of art, all colorized with dates and times, how many hours employee A worked on this project and so forth. So we can map and timeline our efforts. So we can plan and project and all those important parts of the project. But it truly is, it's humbling when you stop back and look at it. So all those have to be addressed. All of them have to be tapped. Some of them tapped a little bit oversized. And there's a stud, a new one, and a stud that we took out. And to get that stud out, the easiest way is most times to weld a nut to it. Sometimes it'll break off. But the only time they break off is when you can't get to them. If it's out in the middle where you can get to them, you spin right out with a little bit of heat. And here's some more work. Some more as we were taking the locomotive apart. Here we have a Hancock top check. This side is for the injector. The hot water pump, and this side is for the injector. And it also has two shut-off valves there. And there's a bracket here that you can't really see, and there was a broken stud right there. And unfortunately, a piece of angle iron got welded to the side of the boiler in place of the stud. The weld broke and allowed that bracket to move. And as a locomotive is in service, it vibrates, as you can imagine. And that pipe moves through the expansion and contraction, the hot water and the cold water, and all of those various things. Well, over time, the feet of that bracket had worn down into the barrel of the boiler. That represents another problem. So we have to assess the extent of that wear, the extent of how thin, the thinnest part of it, and fortunately we're 80 thousandths beyond, we're up above that limit. But still something to address. There's sufficient carbon content in this boiler to where we have to ask for permission. We have to seek authorization to perform welding by the Federal Railroad Administration. The reason that's in place is just to ensure that we're following a process, the correct process. In this case, we didn't have to weld on it. And there's the new piece. We're going to jump forward just a little bit. A new stud. This is an important one because this holds the handrail. And you can see all the various studs all the way back through there. And you can see this bracket. We TIG welded a shim plate to span over the areas that were weakened, that were eroded. So that wouldn't happen again, and we removed those contact points on that bracket. And we replaced the stud. So we removed this broken stud, we cleaned the area of the boiler that had that welded bracket on there, and replaced that stud. Here's some more studs and more brackets. This is part of the support that holds the front of the cab. Those are 3 brand new studs. Now we're going to go inside the firebox. And I remember having more than one discussion with my foreman, and it kind of goes like this. Well, this is what we have to do. And I get a piece of chalk, and then I take that piece of chalk and I walk over here and I make a line up here and around. All of that has to go away. It all has to be cut out. All of those stay-bolts had to be removed. And while we're at it, we're going to replace this. This is the lower part known as the mud ring. Each one of those is a hot rivet, nearly 10 inches long, almost 1 inch in diameter. So a tremendous amount of work. Well, once we get that plate removed out of there, we discover some other things that we're going to have to address. Because this rebuild, we want this to last 15, 20, 30 years. So we have to address all of the things that we discover. We're not just going to restore the engine for 10 years, or we're going to run it a few more times. Everything is done exactly 100%. So when we find something, it's not a matter of, well, I don't think it's that bad. Yeah, I think it's okay. Okay, let's just move on. We deal with it. And sometimes that expands that timeline, that spreadsheet I was talking about. How do you factor in that unknown in that nice Excel spreadsheet I was telling you about? You just kind of, my friend Ed Gerlitz had a saying, you just bow your head and do it. And that's what we do. So this is the mud ring once the plate was removed. And even though the screen has a wave to it, this also had a little bit of waviness to it. For reasons unknown, it had grinder marks in it. Some of the holes with the work was done in a previous life were oversized with a torch or some other device. So we've got to weld that up, and we make a template to the drawing, and we very painstakingly go through and we weld up these variances. The same thing here. This is a condition known as grooving. And this part was not replaced during the last rebuild. The new plate was welded to the old plate. So who knows how old that is? My suspicion is that this is quite old. As the locomotive plate flexes at that point, it undergoes a lot of changes and a lot of stresses. And there's a condition known as grooving that it actually wastes that metal away. Part of it is the erosive action of the water flowing around through there, especially if it's close to one of those blowdown valves. As you open that valve up, that water at 425 degrees, 300 psi is water. As you give it a path to the atmosphere, I mean, it is nearly supersonic in its path out. And it's taking with it all kinds of sediment and debris and other things, and over time it's going to erode the steel. So we've had to clean that up too, and you can't see it, but right in here we've cleaned that up. There were some pretty heavy pits, probably weren't the end of the world, but we've got it apart. So we're going to address that too. So we took and very carefully ground that out, and fortunately that grooving did not extend below that length. This is a big piece of steel known as the mud ring. And this outer sheet is riveted to the other side here. The rivets move through here. So fortunately, that grooving was only present from this level up. And that's not the worst of it, unfortunately. There was some more that was a little bit worse. But as you measure it from the outside with an ultrasonic test probe, you can get an idea of what the thickness of that plate is. Here's a close-up of the grooving. Now we're going to form this plate. We have in our shop a nice big press brake. And part of the philosophy with having a crew, many of which have never worked on a steam locomotive, is that there's an opportunity to serve an apprenticeship of sorts, to train them and help them develop the skills necessary to keep working on the equipment. So rather than source this out to contractors or people that may provide a workforce, maybe the workforce has a skill set, maybe the workforce has people that they borrow from other places, or in some cases a labor force. Well, along with that, when the job is completed, there goes a lot of knowledge on how to work on this. So my philosophy is we do everything in-house, everything we possibly can. And we're going to do it all, most of it, as much as we can ourselves. We're going to learn how to do it. A lot of it, I've got experience doing it, others have done it, or maybe we've read about it. I mean, how often do you drive big rivets? I mean, who around here really does? There's fewer and fewer people with that heavy type of industrial skill set. So we're going to buy the tooling, we're going to source all the equipment, we're going to do it ourselves. And it's darn fun too. It's a lot of hard work. I'm not, everybody understands, I mean, how much hard work it is. So now we're forming this plate, and there it is. So we take this plate, once we got it formed, and rather than drill holes in it once it's there, we take it, we put it on our big mill, and we machine these holes in there. And some may say, oh gosh, that's you guys are such perfectionists. But when you're fitting something together, the closer tolerances you can make, and the more accurate fits you can have for all these welded joints, the better quality job you'll have in the end. Because every one of these surfaces here, this becomes a weld line. We're going to weld that to that piece of plate that we're going to marry up with it. And if we ground it by hand with a grinder, and we tried to be as close as we could get, it's not going to be really exact. And so your weld is going to flow through there. And it's just going to continue to be exaggerated. And what you're going to end up with is something that you may not be happy with. Now we've got that plate fit up in there. And once we've welded all that up, that plate fits right in there. We don't have to heat it with a torch. We don't have to get a come along, a chain. We don't have to get a big sledgehammer. And it fits right in there. Now we're going to ream the holes out, make them all the correct size, and we put in what's called a fit bolt. And that bolt holds that together. And we just, every one of those holes is fit with a fit bolt, tightened right down. And when it comes time to rivet it, we warm everything up, we got our forge out, and it takes all of us to rivet, because there's a job for everybody. We've got, one of my Boilermakers is a great farrier. He shoes horses. He's outstanding. So you can imagine the job he's doing. He's running the forge. And we got a couple people on quality control monitoring the temperature of the rivet, because that's important. It can't get beyond a certain point, and you can't drive it if it gets below a certain point. So the quality control aspect of it, we document that. We have everything, all the I's dotted and T's crossed. And it took, in this case, it was funny when we put together a mock-up, everybody wanted to drive a rivet. I want to do it, I want to do it. When we started doing it, we wanted to do it really, because it's hard. And it's, you know, it's like, I was a machine gunner in the military, and that's the closest civilian thing I've done to holding an M60 machine gun. And I have to say, an M60 was a lot easier than that 90 gun. So it's fun, so to speak. Now we're going to take these Firebox, the corner pieces, and these represent a real challenge, because they're a tapered cone, and they've got two flat transitions offset from each other. So you just can't lay it out, do some geometry, lay out your bend lines, and put this thing in the brake and press it, because it all kind of comes together as this converging cone. And we bought extra Firebox plate, but we just as soon hit it right the first time. So what we did is we got a piece of steel, and I brought a piece of that over here. It's from the side sheet, and we're gonna do some analysis. Austin is great at trig and calculus, and we do a lot of that, because the old books have that. When you go through the Boilermaker layout, and it tells you how to lay this out, there's a lot of geometry in there. Figuring out all the angles, how much does it deflect, how much does it bend. So we go through and get all that figured out. We make a template, and this big frame here is actually a representation of the piece that we're going to put in there. So that top piece is made exactly to the weld line in the top. The bottom piece is exactly the weld line on the bottom, and they're welded together very securely. So now we can take that piece, and we know exactly where to bend it. This particular type of Firebox plate is designed for what we call flanging. It's designed to be formed. So it's a good quality grain structure. It's designed for locomotive fireboxes. It's code material, meaning that it has to have that material test report, and that identification number has to stay with it. Then we make some forming dies, and I brought one of those too. They're quite heavy. We'll draw in CAD these plates, and then we take, when they cut the plates out for us, very accurate, then we'll get the plates back and weld them together, as you see here, and that serves as a press die. You've got a male and a female, and we can use those forming dies in our hydraulic press to now continue to form other pieces opposite what the press brake did. So you can see we broke it this way. We've got all these successive bends. Now we have to curve it. And we do that with the male and female forming die, 75 tons on a 100-ton press, every one of them. And we lay that line out, and we move it through, and you manipulate it by hand, and you make that bend, you form it. And you continue that process. Because not only does it fit like this, at the very bottom it has to bend inward to match up that piece that we've riveted in. Now we're going to weld some lugs on there, because this is about 140 pounds, and we installed a crane inside the Firebox. And this is kind of a conversation we have, you know. We'd like to be able to get it right the first time, but you've got to make a lot of little adjustments. So we put that crane in there, because you lift that thing one time, you're worn out. So we dolly the thing over there, we craned it in and out of there. I bet you one day we had that thing in and out 15 times. And so it's not demoralizing to everybody. You know, I volunteer to stand in there and run the crane and move it up in there and try to muscle it over in position so the other guys can take a break. We just hand fit it and get it in there. There's the other side. And now we've got the back corners and this door sheet piece here. Well, we've got to drill all these complex holes in that sheet that's got all these breaks in it, plus it's on a radius. How in the world are we going to do that? We drilled one of them by hand, and it took 2 of us, and it was absolutely exhausting. One hole. So we regrouped, and a lot of the books we've got a lot of neat machines that haven't been used in years in the shop. We found a device, and we've cleaned up a lot of these other things, and we made an apparatus that will span between the top and the bottom of the boiler, and then we use that as a foundation to hold our air drill. I'm going to go forward here. Here's that drilling operation. We got that drill off eBay for 25 bucks. It was a good deal, and it drilled every one of those holes. It's a steam era rolling motor. It's designed for this. We bought those tool adapters and that specialty cutter. You know, just trial and error. You know, just kind of another little side note. Sometimes we'll make tools, we'll have an idea. We had an idea we were going to make this tool that could draw the cutter in from the outside. And one of us could be on the outside operating a handle on a threaded shaft that would draw the end of that cutter. We spent 4 hours making it, and it broke in about 10 seconds. And so that's demoralizing, but you just regroup, and you've got to find a way to do this. You know, we're not going to get in there with a drill and do it all haphazard. I mean, we're really going to try to make this, because like I said, this is a 30-year rebuild. I've got about 12, 15 years before I can retire. I tell Austin, my foreman, and others on my staff, you know, next time we see this, you're going to be my age. If we do this right, you won't have to be into this kind of work until you're where I'm at in my career. So that kind of motivates us to stick with it. So back to this shot here, we've got all those holes drilled, and you can see they're all in a pattern, and each one of those has a corresponding hole location on the outside, and I'll show you what goes in here next.